Hello, and thank you for coming for this presentation on slanted etching of high-R materials using reactive ion beam etching. I'm Dr. William Frost from Oxford Instruments, and this is some work that we've done in conjunction with EV Group in Austria. So a little bit to start with Oxford Instruments. A spin out from Oxford University in the UK. They're involved in a wide number of material science, from deposition growth to analysis, research and discovery, areas such as EDX technology, and we're involved in the earliest superconducting magnets and implementing them into measurement techniques such as VSM. Specifically at Oxford Instruments Plasma Technology, we work on things like growth and deposition of thin films with a wide range of techniques such as plasma-enhanced CVD and atomic layer deposition. And also we do a lot of etching that we're going to be talking about today. This is using ICP and RIE etching, atomic layer etch, or ion beam etching. The etching we're going to be talking about now is waveguides. And these waveguides for augmented reality glasses. These glasses often have two waveguides, an input grating and an output grating, and they come in a variety of different shapes. These shapes could be something like the one shown on the right, with our linear binary grating, some kind of sawtooth blaze grating, and a slanted grating. But for the optimum efficiency, we want to be using the more tricky geometries there, the blazed and the slanted gratings, and this takes a bit more fabrication. But as you can see in the SEMs on the right, we at OIPT and others do successfully manage this kind of fabrication. It's not just the geometry we need to consider though, it's the material itself. So currently we use polymer-based resins. We can make a stamp via lithography and etching and stamp a grating shape into this resin, and that gives us our waveguide. This is a permanent resin layer. The resin is placed, stamped, and becomes our product. But they only have refractive indices from 1.6 to 1.9. What about if we want to increase our field of view, for instance, and we want to go higher with our refractive index? Well, then we have to move on to a solid state material, something like a high RI glass or a metal oxide, like titanium dioxide. But of course, these cannot be directly stamped in the same way as a polymer resin. So instead, we have to do our stamp into a resin as a sacrificial layer. The resin now acts as a mask to allow us to etch the final product. So we're adding on another fabrication step at the end to allow the use of these high RI materials. And we can do this using ion beam. So let's summarize that fabrication process. So a nanoimprint process by someone like EVG, using one of their tools shown on the right, we can stamp our substrate, cure the resist, and demold it. And now we have our sacrificial resin layer ready to be used as a mask. Now, using something like the ion fab from Oxford Instruments, we can descum the film and open up the mask. Use the etching to get our slanted etch or whatever geometry we're trying to achieve, and then strip off the resist for our final product. At Oxford Instruments, we offer some different solutions for this as well. So the mask opening could be very effectively done using ICP etching, something like a Plasma Pro 100, a little example there shown with a chromium mask opening. And then of course at the end, if you want to add a little bit more resilience to your final product, you could use something like ALD in our Flexol system and deposit something to stop mechanical or chemical degradation of your grating. So why ion beam? Why use this reactive ion beam sputtering versus a conventional ICP? Well, on the left, we can see the conventional ICP system, and everything's in one chamber. We generate our gas, draw the plasma down towards the table using a bias voltage, and this is going to be orthogonal to the surface. We're going to have a perpendicular etch direction. So if we wiggle the table around, tilt it, move it around, we're just going to get that perpendicular etch no matter what we do. In ion beam sputtering, we've separated off the plasma generation from the substrate chamber. They're two different areas. The plasma is generated in the same way as an ICP, but then using a series of grids with different voltages, we accelerate and collimate a beam of ions. These ions now have a direction of travel that they're not going to deviate from. So now we can, as on the right, move our substrate around, and get different effects off the orthogonal direction. And this leads us to be able to do things like slanted and blazed grating. So that's why we have to use ion beam for this technique. This isn't limited to one or two materials, and here are some basic examples. Something like a silicon oxide etch, a deep silicon oxide etch, 3 microns with a slanted edge, towards 3-5 facets with indium phosphide there, and also isolated holes as opposed to a continuous grating shown in silicon. The other advantage of this technique is moving from small single molds on one 100mm wafer up to a larger wafer. The uniformity of the etch within devices and across the wafer is good enough to produce 10 of these on the 200mm wafer. Since we're adding in another fabrication step, this increase in efficiency is a great way to reduce cost and really make this a viable technique. So let's look at some actual examples here. Let's look at what we've done. So we can see there are 200mm wafer with an array of gratings on it, ready to go after nanoimprinting. The central SEM shows them after the imprinting, and we can see that we have this sacrificial resin mask on top with a little scum layer between them. So that's what we need to remove first. Then we can see beneath that some titanium oxide that we want to etch. So we use the ion beam to descum the wafer, and that gives us the result at the bottom right. We can see we have a nice smooth titanium oxide surface ready for etching, and we haven't changed the critical dimensions or the fidelity of the mask in any particular way. So we don't need to worry about defining our mask for damage. We can get a nice clean descum and mask opening process. And now we are ready to do our etching. And this is what we achieve. On the far right hand side, we can see an SEM image of a lovely 50 nanometer titanium dioxide grating with parallel walls around 50 degrees. This wall angle is manipulable with fine control. You could go up to 90 degrees and do your normal binary grating, or you could even come down more acute. These walls should be nice and parallel and with a good quality surface, but we do need to have some considerations there. Mask thickness will have a significant effect. You're going to have a lot of shadowing, and also the angle of your walls is going to impact what happens in your etch. So carefully designing your mask and carefully opening your mask are two very important steps. Because of this, selectivity is also a big concern. Whereas in an RIE, we might be using 1-to-1 selectivity. In the ion beam, really you want to be above 4, so you can have a nice thin mask. And in the example shown on the right, where we have this titanium oxide, this high RI material, we've got a 5-to-1 selectivity to this nanoimprint resin. This can also be applied to high RI glasses. So here we can see a comparison of a standard glass to an N1.9 glass, something that would give us an improved field of view compared to the current resins. And you can see in the far right hand side, we've managed to mimic the behavior in the standard glass in the high RI glass. Of course, there are some hiccups. Changes in the structure of the glass and how it behaves means that we get changes in things like etch rate. It's not quite as easy to get that perfect grating that we're looking for. But we still benefit from the improvements in the selectivity. So it's an exciting avenue of progress that's still ongoing. In conclusion, we've said that RIBE, and we've shown that RIBE can be used to create granted etchings in high RI materials for improvements to augmented reality glasses. This is true of oxides and glasses as well. Of course, this is all a work in progress, and not just with the etching technique, but also in the materials. And at Oxford Instruments, we are working with materials manufacturers to come up with more advanced materials so we can continue enhancing these gratings, both with the etch and the basic materials. Thank you very much for attending this presentation. Please feel free to direct any questions to me at my email address. See our 2 websites for further information on the actual process and the products themselves. And the full work for this was presented in a paper by Martin from EVG. Thank you very much again.